So we're talking about hypothesis testing today. The Q test, the Z test, the T test for equal means, and the F test for equal variances. And we're going to also, in doing those tests on a set of data, we're going to explore what we mean by hypothesis testing. So we're definitely going to talk in great detail today about statistical hypothesis testing, which is really important for forensic scientists to be good with. So if you're going to use statistics to make decisions, then this is how you make statistically defensible decisions. So that's the next several lectures are incredibly important. So when you come in, go ahead and type your username into the chat so that I can see that you're here. So go ahead and do that now if you're online. And so let's get started. So this is the scenario for today. DW Labs is hiring a new person. Okay, and we also have a forensic chemist on board that we want to recertify in the analysis. So we have two people that we're going to compare. We go to the vault, and we pull out a recent seizure that's been analyzed carefully to be 13.2% cocaine by mass. Either it's a library standard or we have enough experience with this library sample that's sort of the average and standard deviation of all of our previous measurements. So that's what we would call the true value. Although the word true value is difficult to use because we really don't ever know the true value. We have the accepted value. So we're accepting that that value represents this cocaine sample. And so we'll call that the true value, but it's really the technical term is the accepted value for the concentration of cocaine in this set of samples. And so we have the trainee and the forensic chemist analyze these samples 10 times. So each person has 10 data points, and we're going to analyze those 10 data points the whole time. Now, we're doing this because we want to know, is each person accurate? Is each person precise? And are they the same as each other or different? So does everybody understand the scenario that we're doing? So we're just sort of testing our own lab personnel to see how well they perform on this analysis. And so here's the perfect scenario. In a perfect world, there'd be no statistically significant difference. Now there's always going to be a difference between two analysts, but is it statistically significant, right? So we want to make sure that if I give the sample to anyone in the lab, I get the same answer plus or minus a certain amount, but they're both just as dependable. You know, they won't be exactly the same to whatever decimal place, but they'll be from the same population. So I have a true value plus or minus some variation. And I want to make sure that if I give that sample to anybody in the lab, I get an answer that's from that population. Okay. That there be no statistical difference in accuracy. So I would get essentially the same answer from each one, and there'd be no statistically significant difference in their precision. So I wouldn't have one analyst that was more precise, significantly more precise than another. And then, and this is just the way we would like to work or operate. You know, that'd be in a perfect world where I could just hand it to anybody and be dependent upon your results. Okay. So here are the data points. It's always important to just take a look at the data to see if there's anything strange about it, if it's good at all. Move this screen sharing stuff around. Okay. And so here we have our true value or accepted value down here at the bottom. And we have the trainee column and the forensic chemist column. So what are your opinions on the data?
Trainee has a little more variance, while the chemist is a lot closer to the accepted value. Yeah, so good observation. You see the forensic chemist is 13s all the way down. That's good. So you just kind of start with the least significant digit, the most significant digit, the 10s, and they're all in the 10s place, they're all in the 3, you know, it's all 13, and it only changes in that 10th place. So that's pretty precise, right? It's all plus or minus, less than plus or minus 1, right? Whereas the trainee, what's the minimum value for the trainee?
11.5 and the maximum 15. Yeah, so it's a big spread from 11.5 to 15. So right there, just looking at the data, you could say, well, there's a significant, likely a significant difference between the trainee and the forensic chemist in terms of precision. Precision is how much the data scatters. So without doing any statistical analysis, you can just look at the numbers and say, yeah, it looks like the trainee's a little bit more scattered than the forensic chemist, and it kind of makes sense. Okay. It does look like they do surround the true value though. So accuracy, you know, it looks like both of them could be accurate. Okay, so we'll have to do a little bit more looking for these. Let's look at a graphical method. So a lot of times the first thing you do is plot the data. Now you can plot the data in Excel, you can do a scatter plot. But like I said, I'd like to show you some of the power of the statistical packages like Minitab. And so, let's see. So this is an individual value plot or a dot plot that Minitab has. And so again, we have the three questions. Are they the same? Are they accurate? Are they precise? And I've got some blanks here that you can fill out. So let's handle those questions, you know, separately. So the very top question, are they the same? Can we look at these dot plots and see if they're the same? Or would it depend upon who I gave the data to, or the samples to? See, when you plot out the data points, you can really see the differences, can't you? With respect to precision, are they the same? No, you see how much scatter there is on the trainee. Those red dots are all their individual measurements. You see the 15 way at the top and 11.5 down at the bottom. And then look at the forensic chemist on the right. You know, their data is all clustered within plus or minus 1. And then the true value is shown on there as 13.2 plus or minus 1. So those yellow bars are the plus or minus 1. The green bar is the 13.2. And so that's how we test the accuracy. So are they accurate?
And the chemist is more accurate.
Yeah, the forensic chemist is more accurate. It has the correct answer 4 times in a row. You know, and one standard deviation low 3 times. And then it's got 3 data points up above. And so it looks like the forensic chemist is right on top of the true value. The trainee, it looks kind of like they were biased a little bit low, but then that outlier helped them, you know, push their average up. So they do kind of surround the true value. So what are the benefits of graphical methods? So let's discuss that for a second. What is this? I mean, describe your understanding of this chart or ask questions about it. You know, what is the benefit of this chart?
It's easier to interpret.
It's very easy to interpret. Yeah. By that you mean?
Like you can see it. It's not just a list of numbers. It's just a row.
Yeah, it seems more obvious when you have it charted. And so I think that's the benefit of a graphical method. It really is that a picture is worth 1,000 words. You know, and if you can show it on a graph, then you can spend 1,000 words explaining what you see on that graph. But most people, you're just confirming what they already see or drawing their eye to some of the main points on the graph. So this is a dot plot or an individual value plot. Those are labeled up there, you can see. There's another kind of plot called a box and whiskers plot. Now, sometimes if you have too much data, this thing can be not so easy to interpret, right? You just have big red clumps of data. And so you can combine all of those individual values into the minimum value, the maximum value, the plus or minus 25 quartile, the mean and the median. And that's what you get here is this box and whiskers plot. So this is a box plot. And so notice there's no individual data points. It's just the mean, the median, the middle 50% data points are inside that box. So 25% of the data is below or above, and then 50% of the data is in the box for each of the analysts. The line in that box is the median. You see it's labeled here. And then also it does a 95% test or confidence test on the outlier, on any of the outer data points. And so this is telling us that the trainee has an outlier, a statistical outlier. We'll understand what that means in a minute. Okay, but that's also nice in terms of the box plot, the individual value plot. That 15 was up there, but it wasn't labeled as an outlier. Okay. And so again, we could look at this and say, are they accurate? Why would you say that they're accurate in this case, if you were going to say that? What piece of this plot would you look at to say, oh, well, they're accurate at least?
The true value.
Yeah, you see the true value, but what is the individual person's data? How does it interact with that true value? What do you see that could lend you to make a judgment on accuracy?
That top 25 percentile is like closer to that green line.
Yeah, you're on the right track. Can anybody else say it in different words?
Maybe like how close the median is to them.
Yeah, the median would be here. The median's pretty low compared to the true value on the trainee. So that might be a discussion on how it might not be as accurate, but certainly not as accurate as the forensic chemist. But what about the trainee does contain the true value?
The 75% quartile.
Yeah, or just the box, right? That box contains the middle 50% of the data. And if that box intersects, or the true value intersects the box, then they may not be the best at accuracy, but they're accurate enough to get it inside the box, right? So if the box in the true value, if the true value is in the box, you're moderately accurate at least. Okay. If that true value was outside the box, then your accuracy would be poor, very poor. Okay. And so once again, a graphical method, very quick to interpret. Okay. I don't think that the trainee has great accuracy because that true value is right at the edge of the box. It's not in the middle of the box. It's nowhere near the median. Okay. In the middle of the box is the mean. So the little connected line, that's connecting the means, and then the median is drawn as its own line inside the box. And so that's what that little data point that's a cross data point with the line connecting them, that's connecting the means in this particular plot. Okay. Very good. And a couple of people online answered well too. Okay, so these are the graphical methods. But what is the issue? What's a problem with graphical methods? Yeah, it doesn't. You're right about it not representing precision. What is a better way to represent the precision?
I would go with the box plot one, but the problem with that one is that the limitations of the data. You can't do large sums like if you do repeated tests over and over again. Eventuality, the groups will just overlap, like you said, and just produces like that. And kind of the same problem with the box plot.
I would just say the standard deviation.
Yeah, so you're looking at this and you want a number, don't you? Right, and that's the problem with graphical methods, is they don't give you a number to make a decision on. Right, so sometimes, this allows you to evaluate it in general, but sometimes we want specifics. We want to be specific. Is this above or below a certain threshold? Right, is this statistically significant or not? When you're going to have to make a decision like that, you need a number and you need a bar. Is that number above the bar or below the bar? And so the problem with graphical methods is they don't give you the numbers that you need to make a decision. Okay. Now, sometimes, like if the true value was outside the box, you can make a decision on the precision and say, look, they're not precise, okay? Even without a number. But if it's at all in question, you need the number to know if you're above or below the decision point. And so let's talk about these decision points, this hypothesis testing. Okay, so looking at the data, we need to do some manipulation on the numbers. We need to collect the mean or average value, the range, the standard deviation. So these are some what we call figures of merit. Let me write that on here. Okay, so they tell us if this data is good or not, right? So, you know, like the merit badge, you did good, you got the merit badge. This is a figure that tells you, did you achieve accuracy or precision or not, right? So you need these figures of merit. You know, a mean that's close to the true value is a good thing. So that's what we mean by figures of merit. A narrow range or a narrow standard deviation is a good thing. That's precision. And so these are the figures that tell us if you're doing well or not. And so we can compare that mean and the standard deviation to the true value to see. And so the question in terms of being accurate is, does the average or the mean plus or minus the standard deviation contain the true value for the trainee? And so we can look at this 12.9 and we can look at plus or minus 0.9. And so if we look at this just plus or minus one standard deviation, it goes from 12 to 13.8, and 13.2 is in between those two numbers. Okay, so we can say that they're moderately accurate, right? That the true value is within their error bars, at least within one standard deviation, which is better than two standard deviations. So they're, you know, we would say that they're fairly accurate. And then let's look at the forensic chemist. They have 13.3 plus or minus 0.2. And so that goes from 13.1 to 13.5, and 13.2 is in between that. And so they're both, again, accurate. That's what those boxes were indicating to us on the box plot, that they both contain the true value. And so they were accurate. We don't really have, except for the standard deviation, a judgment on their precision, but we could do the relative standard deviation, right? We could take their precision number and divide by their mean and see what percentage that is for the coefficient of variation. So we'll do that next. But here, the very simple, this is the basic statistics that you learned in quant, right? Take the average, take the standard deviation, see how it turns out. And so numerically, both of them seem to be accurate because their means and standard deviations contain the accepted value. Now, you can't know this unless you have some standards. So that's why we test ourselves. We'll test ourselves against a known. And that's what this is. This is sort of a verification that our technique and our analysts can get the right answer. And you have to do that before you really look at evidence or unknowns. So you want to verify that you get the right answer when you test yourself against a library sample or a known sample. Okay, so let's look at this hypothesis testing, because we need to make a decision on precision, and then when we compare the two analysts, we need to make a decision. We want to analyze that data point number 15, or for the trainee. And these are examples of null hypotheses, and this is our null hypothesis judgment table or error table. If we have a true value and so on, we really can't know which is true or false. We can only know these two things. We can know if we reject it or fail to reject it. And so if we fail to reject the null hypothesis, that's what H0 means, okay? If we fail to reject it and it's true, then essentially that's what we're saying. We've accepted it as true, but the terminology that we use, we fail to reject the null hypothesis. And if it's actually true, then we've made a correct decision, okay? If we reject that null hypothesis and it was in fact false, then we've made a correct decision. Okay. But if we fail to reject it and it was actually false, we've made a type 2 error. Okay. And if we reject it and it was actually true, we've made a type 1 error. So these are well-known statistical categories. Notice we talk about type 1 or type 2 error, not false positive or false negative, because a false positive and false negative have to do with how the test is phrased. Okay. So if you're testing for cocaine and it is actually cocaine and you fail to identify it as cocaine, then that would be a false negative because it really was, and you failed to identify it as, or if it really wasn't and you identified it as cocaine, then that'd be a false positive. But again, you have to see what the language of the test is, how it's stated to know if it's a false positive or a false negative. You don't need to know anything about the test to understand it if you talk in terms of the null hypothesis. Okay, and so you always need to fall back on this table to say, what is the null hypothesis for this test? And then you can define what a type 1 error and a type 2 error is. So today we're going to cover these null hypotheses. The data point is not an outlier. Notice it is a statement of fact. That's your hypothesis, and that's your baseline hypothesis. And then we're going to do statistical tests to see if that null hypothesis is true or not, or if we want to accept it or not. Here's another one. The trainee and forensic chemist data sets are from the same population, meaning they have the same mean. So we will test that null hypothesis using the t-test. Okay. This first one we will test using the q-test and the f-test. No, I'm sorry, the z test. And then this one, the same population, we'll use the t-test. And then the last one, the trainee and forensic chemist data sets have the same variance. Remember, variance is your standard deviation squared. And so that's your precision test. So that would be the f-test. So these are the 4 hypothesis tests that we're going to use today. Well, we need to pick it up a little bit. Okay. If I ever go past and you're still writing, remember you can go to Zoom and fill in your notes if we leave you behind on certain things. Okay, so let's look at this, how we use hypothesis testing. So we make decisions on the null hypothesis using our confidence intervals. So if the probability of the null hypothesis being true is less than 0.05, then we reject the null hypothesis. It's a pretty stringent test. So it's got to be less than, if the probability is less than 5% that the null hypothesis is true, then we reject it. Okay. And so we have to have a pretty strong test before we reject our null hypothesis. Think about that. If it was only 6% that probability that it was true, we would keep it. Okay. The 6% chance that's a true hypothesis, we'll go ahead and keep it. We fail to reject it is the way we say it. Okay. Now this 0.05 is alpha. So that's our alpha value, 0.05. And you hear us talk about confidence all the time. 1 minus alpha is our confidence. So whenever we have an alpha of 0.05, we're talking about 95% confidence. Okay. What would be alpha if we wanted to be 99% confident? 0.01. Yeah. So you understand. Yeah. So we're dealing with this whole lecture today is all dealing with an alpha of 0.05, which is 95% confidence. Now, when it goes to 2 tails, we could be high or low. It's 2.5% on either side. Okay, so it's still 0.05 alpha, but sometimes we divide alpha by 2 if we have a 2-tailed possibility. Okay. And so this really depends upon your null hypothesis. If you can't state it clearly and concisely, then you have no business doing statistics. So if someone's talking to you about statistical testing, you need to pull the thread and say, well, what is the null hypothesis for this test that you're doing? If they can't state it, then your little alarm bells should be going off in your head, okay? Always be gracious. There's never any reason to like call somebody out or be rude, but your confidence in their analysis is dropped dramatically if they can't state their null hypothesis. And guess what that means? My confidence and anyone else's confidence in your use of statistical testing drops dramatically if you can't state your null hypothesis. Okay. And in PChem, we use p-values all the time for the M and B. And all of those other coefficients that we used, we were using hypothesis testing. We wanted that p-value to be less than 0.05. And the null hypothesis was that M and B were just randomly generated from the noise. And so if there was a 0.5 or greater chance that M and B were generated by noise, we just ignored them or rejected them and redid the analysis. Most of the time it's the intercept. If the intercept is, and we'll see that next time. So for today's test, we're testing the outlier and whether they are the same accuracy or the same precision. So here's our Dixon's Q-test. Let's look at the data points in our particular analysts, and we'll look to see if that 15 is an outlier for the trainee. So Dixon, now notice that you can throw a data point out if you spilled it. If you're pipetting something and you see that there's a big old drop left in the pipette tip for whatever reason, or you've got water in your pipette apparatus or some kind of thing that's totally screwed up that particular data point, stop what you're doing, throw that data point out and do that one over, okay? You do not have to take junk data through your analysis because garbage in, garbage out, okay? But if you've done everything and you didn't see anything to cause alarm and yet you still have a 15 and everything else is 13 and below, then you want to look at that 15 and say, is that statistically reasonable? Is that from the same population? I mean, you know, your data spreads out as you analyze it, but what is the likelihood? Is it less than a 2.5% chance that I would get a 15 when all my other data is down here? That's what we're asking. So our null hypothesis is that our question data point is not an outlier. And if there's a 6% chance that it's not an outlier, we'll keep it. But if it's less than 5, or I should say there's a 5% chance that it's not an outlier, we'll keep it. But if it's less than a 5% chance that it's not an outlier, then we'll throw it out. And how do we decide whether we should throw it out? We don't use a graphical method, we use numerical methods. So we calculate this Q experimental value and we compare it to a Q critical that comes out of this table here. So this table has our varying alphas and our levels of confidence. So we're dealing with the 95% confidence or an alpha of 0.05. And we've got, for the trainee, we've got 10 measurements. And so this is our Q critical value. And so then we'll calculate this Q experimental. We'll take that 15 and we'll subtract the data point that's next to it. I think the next highest one, we'll have to go look at the data. Let me pull it up real quick just to see. 13.3, okay. So this next nearest value was 13.3. Let me get the range.
The lowest is 11.5.
3.5. What's that?
Saying the lowest value is 11.5.
3.5, yeah. Yeah, I guess we could have written that in there. So you could just put the range down here, or you could put 15 minus 11.5. Thanks. Yeah. So look what we're doing. We're comparing the gap to the range. The gap between our question data point and its nearest neighbor and comparing that to the range of the data. And so then that's our Q experimental. And we compare that to this. let's go ahead and calculate it if you don't mind. So 15 minus 13 would be 2, but this is 1.7, right? 1.7. And this is 3.5.
Negative 0.485. The next number is seconds, so it's 4.86.
Sorry? Yeah.
0.486.
486, okay. 486. All right, so we've got a Q experimental of 0.486, and look at our Q critical, 0.466. And so 486 is greater than 466. Then our null hypothesis fails. HO fails. So we reject that this is not an outlier. It's a double negative. All right. So that means it is an outlier. Okay. So it's likely an outlier. So we would say that we reject our null hypothesis. So what do we do with that? Well, then we redo the mean, we redo the standard deviation and everything without that data point. Okay. Let's test it with the z-test. So there's two possible ways to test the q-test. I've asked around, and the only people I've ever heard use the q-test are chemists. You're a forensic chemist, so you may come across it, you may continue to use it. Here's the pedigree for it. It's in this Analytical Chemistry Journal in 1991. So that's the article that tells you where that table came from. Okay. But the Grubbs transformation, or the Z transformation, is recommended by the International Standards Organization or the American Society for Testing and Materials, so ASTM. So this, in many other disciplines, is the preferred test for an outlier. Okay. So once again, if there are no known reasons for producing the outlier data point, then you can use this to test to see if it's an outlier. It's based on a Gaussian distribution that has a mean of 0 and a standard deviation of 1. So what we've got to do is take our data point and transform it over into this idea of the mean being 0. So we subtract the mean. So our data point's deviating from our mean. By subtracting the mean, we're saying, how does this data point deviate from 0? Okay. And then we're dividing by the standard deviation, which is essentially a way to scale it, so that we're dividing it by putting it in this category of a standard deviation of being 1. So we're scaling it by our standard deviation and calculating our Z value for our question data point. So we have our 15. If you could look back in your notes, tell me what the mean was for our number.
For the trainee,
Yes, please.
12.9.
12.9. And the standard deviation, 0.93? Okay, so let's go ahead and calculate that one. So that would be 2.1 on top, correct? And divided by 0.93. All right, 2.26. So this is saying that it's 2.26 standard deviations away from the mean of 0 and the standard deviation of 1. Okay, and for 95% confidence, 95% of the data would be within 1.96 standard deviations. And so this is saying that it's less than a 5% chance that it would be that far out if we had a Gaussian distribution of data. So again, we have our null hypothesis that the question data point is not an outlier. 15 is not an outlier. That's our null hypothesis. But if 2.26 is greater than 1.96, then reject HO. And so we reject it. So both tests for the trainee give us that it is an outlier. Okay. This 1.96 is so common anytime we're dealing with this normal distribution that it's a number that you should essentially memorize. So whenever you're making a 95% confidence interval, you multiply your standard deviation by 1.96.
But does that only work for the values points from that, the standard deviation or the statistics table, it has to be such a large number of samples, right?
Well, yes, we still use this in terms of our 95% confidence intervals. Now we could do there's a way to do a sample like using the t times s over the square root of the number of data points. Yeah. Okay. A lot of times, this is a great point to bring up. A lot of times we are using like a calibration curve and so on. So we have a lot of information about how the system behaves. And so that gives us the ability to use Z. But like if you're just doing 3 measurements, like 3 titrations or something, then you would use that T value to come up with your sample confidence intervals. Yeah. I'll have to find a place to put that in the notes to be more specific. Yes.
Whenever you were describing the Z values, you said that it means that the point is less than 5% chance away from a, can you just say that?
Yeah, so let's go ahead and draw this little curve here, 0 and our Gaussian curve here. So we have a mean of 0 and a standard deviation of 1. And so way up here, this would be 1.96. Capturing 95% of the area under this curve. And our data point came in at right about here, 2.26. So we're actually calculating what this Z value is. So this is Z question mark. It's the Z for our questioned data point. And so if it were less than 1.96, it would be inside this curve, right? But it's above 1.96. And so we're saying it's really less than a 2.5% chance that it would be, that high. In fact, you could, there's a way, I don't know exactly off the top of my head, how to turn this 2.26 into a percent or a likelihood. Okay. But I just don't remember off the top of my head.
Yeah,
I could look it up, but
it's right on to my tongue.
yeah, but see how much higher it is than the 1.96,
Convert it to the p-score.
Yeah.
Do it that way.
Yeah.
Yeah, you have to convert it to p and do all. Yeah, I know what you're talking about.
Yeah. But we know that it's less than the 0.05 or actually 0.25 because 0.25 is on the low side too. And so here's our, and I just for convenience too, I put the highest data point for the forensic chemist and the nearest neighbor on the same rows, just so I could copy the formulas over. So I went ahead and did the Z test and the Q test for the forensic chemist too. This is their maximum value and this is their nearest neighbor. And so our Z test for the trainee came in here at 2.3. Our two-tailed T value was less than that. And so our conclusion was that it was an outlier. Now this 13.7, when all these other values were so low, the Z transform came in as making that one an outlier for our forensic chemist. But look at the Q test, it says it's not an outlier. So, exactly. Right. So we go, what do we do in this situation? Okay, we keep it. Remember, the null hypothesis is to keep it. And so if there's any ambiguity about that data point being an outlier, we keep it. And so in this case, we have conflicting tests, and so we keep that data point. It's got to be clear and convincing statistical evidence that it's an outlier for you to throw it away. In other words, less than a 5% chance that it's within that population. So, but the outlier, it was an outlier for both tests for the 15 on the trainee. So we need to redo our mean, our standard deviation for all of those trainee data points. In the rare case that you had a really low data point too, and you thought you had 2 outliers, it's hard to do that, but it could happen, theoretically. You would do the outlier test on the furthest data point first. get rid of it if it's really a bad one. And then you would redo all your statistics and then test again on the low point or the nearer outlier. But when you throw the first one out, it gets more difficult for the second one to be thrown out. Okay. And so you could still do it though, but it gets more and more difficult as you try to do that. Yes.
Since you're throwing out a data point, you said there's 2 outliers. You throw that one out, but you have to reduce the sample number as well.
Yes.
Or you keep okay.
And that also makes it more difficult to get rid of the second data point. Yes. Now this is all predicated on continuously variable data. Remember, I pounded that into you over the control chart. If you have gas prices where you have so many data points that are the same day after day, and then you have a couple of data points out, those statistically will be outliers because you have the same answer so many times, the same exact answer. So you can't do these Gaussian statistics on data that jumps like that. And that's why I say it's invalid data. It's category data, not continuously variable data. So all these outlier tests are based on Gaussian distributions on continuously variable data. So if you have things that jump like categories, you can't use these statistical tests on them. So you really just need to find a more precise way to measure that data point because it really isn't the same every time. You just aren't capturing the variability. So let's look at our accuracy and precision without the outlier. Okay. So our accuracy with the outlier, we would say is fair, right? It's 2.5% error. So we just take the, here's the error calculation, our mean minus the true value. Notice the order. Why do I want the true value to subtract the true value from the mean? If my mean is lower than the true value, I want that number to be negative because the negative implies that you're low and positive implies that you're high. Make sense? So it matters which one you subtract from the other. And so your mean minus the true value or your mean minus a literature value, so that when your mean is lower than that value, you see a negative number. When your mean is higher, you see a positive number. Okay, same like today minus yesterday in our control chart, or yesterday minus the previous day, because if it goes down, it needs to be negative. If it goes up, it needs to be positive. Okay, think about the reverse. If it went down and it was positive, that'd be weird. And if it went up and it was negative, that'd be weird. If you reverse the order, your signs are flipped and it's confusing. Okay. Same with percent error. You take that difference and divide by the true value times 100%. But again, the order is, again, the true value is being subtracted from the experimental value. And so that's what we have here. The trainee is negative 0.33. Its mean minus its accepted value is low by 0.33%. And if you divide that by the true value, that's 2.5% low. And I call that fair. So up here's a little table for the language that I'm using. There's no real standard for this, but this is my criterion. If you're less than 5, if you're greater than 5% off, or if you have greater than 5% precision, I call that poor. You should be within 5% of the true value. Otherwise, your accuracy is poor. But if you're 2 to 4.9, then that's fair. Okay, you're within 5%. That's not bad. If you're within 2%, I'd call that good. And if you're within 1%, I call that excellent. So these are just my categories that I use. But it's always good to define your categories. If I'm going to use words like to say your accuracy is fair, you need to know what I mean by that. Okay, and then here's the precision. So if we take that standard deviation and we divide by the mean and calculate the RSD, and then we I just for grins calculated the population standard deviation. Even though this is only 10 data points, I'll say just for grins. But it's not used in any other of these subsequent things. So yeah, I put sample here, RSD for the sample. That means I'm using this number here. This number is going into this value here and this value here. Okay. So 7.2% precision. So I would call that poor precision because we're including that outlier. Let's see what happens when we kick that outlier out. So we take that 15, that result of 15, and we get rid of it and recalculate our mean. Now our mean is dropped to 12.6. Okay, this chat window is kind of in the way. Our range is 1.8. Our standard deviation is 0.58. It went from 0.93 to 0.58. That's fantastic. Okay. But because the average dropped up here, the 12.6, we got worse. We're still within 5% though. So we still have fair accuracy. Okay. But then our CV has gone up to gotten better to 4.6. So we really didn't lose that much in accuracy, but we gained a lot in precision by getting rid of that outlier. We went from 7.2% coefficient of variation to 4.6%. And so we're now in the fair range of precision. Okay. Let's look at the forensic chemist. So they had the accuracy, their average was 13.3. And you calculate their absolute error was 0.07, the percent error was 0.5. So that's excellent. That's less than 1% error. And they're just a little bit high, 0.5% high. Now I know it's high because this is a positive number, right? So that tells me that they're high by 0.5%. Okay. And then their precision is good. They're down here at 1.5% CV, which is in this range of good precision. Pretty cool, huh? So we're looking at it. We pulled out that outlier. Some things improved, but notice that now our range, this goes up to 13.0, and it does not contain the true value. So we're missing it just a little bit. The true value is 13.2, and our trainee is now biased low. We're actually capturing that it's biased low. Okay, so we're missing that true value quite a bit. So something in that trainee's procedure is causing them to come low every time. So we need to analyze it, see how they do their standards or whatever their way they're analyzing the data, because they have a bias. They're, on average, they're 2.5% low. So in order to report the standard deviation for the whole lab, that includes the standard deviation from both the trainee and the forensic chemist. Let's say as a lab manager, I was happy with this, even though they're not excellent in terms of precision. I'll go with it. I want to produce a standard deviation for the lab. I need to pool those standard deviations. And so this would be the weighted average of the variances. So if 1 is the trainee, then we have 9 minus 1, 9 minus 1, and 10 minus 1, and 10 minus 1. So we have the variance for the trainee times its degrees of freedom, and the variance of the forensic chemist times its degrees of freedom. Okay. So this piece right here is the forensic chemist. And this piece right here is for the trainee. And these n-1s are all the degrees of freedom. So it's just whatever data points that they have minus 1, those are the degrees of freedom. And then we would use this pooled standard deviation to do the t-test for equal means. And so we would come up with an experimental t-value using the means for the forensic chemist and the trainee. And we would have, again, 9, 10, 9, and 10. And then this pooled standard deviation would go in the denominator. Okay, so this is how you would come up with the t-test for these two personnel. And so the hypothesis, the null hypothesis for the t-test for equal means is that the trainee and the forensic data sets are from the same population. It's a fancy way of saying they should get the same answer. Okay. So we calculate t experimental using our equation. And since our trainee could be high or low, we have what's called a two-tailed t-test. And so we divide our alpha by 2. It's half of 0.05 or 0.025. And this is a great way to calculate those t critical values using this function in Excel. So the degrees of freedom of 8 are for the trainee, right? So we use the worst case of the two. So we picked, since the trainee had fewer data points, we used that degree of freedom. And so this is 9 minus 1. All right, we threw out that outlier, which gave us 9 data points for the trainee. And so this would be the worst case degree of freedom, which would be 8. That's going to give us the highest t critical value. It's going to be the most conservative test for this null hypothesis. And so if t experimental is greater than t critical, then we would reject the null hypothesis that they have the same accuracy or that they're from the same population. Now you can look these up in tables as well, but I prefer to use Excel. It's right there on your computer, and just use the t inverse formula. This is from NIST. You can just type in students t distribution and you'll get 1,000 sources for it, but Excel is right there too. And I don't trust to produce these tables, although NIST is pretty trustworthy. I'd rather calculate it myself using Excel. So here in Excel, we have our means, our ranges, we have our sample variances. So the standard deviation squared. So this is a S1 squared. This is, oh, sorry, that's for I went ahead and did it both with the outlier and without. So this is also S1 squared, and this is S2 squared. Okay. I calculated the pooled standard deviation in both situations, and then I did the t-test, the experimental t-test for these. So this is t experimental, and this is that t inverse value. This 9 one is for that value over here. Okay, this one here is let's see, this one is t inverse 0.025, comma 8. And so then we have our t-test here. We have 2.83, and that's greater than 2.69. And in this case, we have 6.74 is greater than 2.75. So in both cases, t is greater than the t from the table, or t critical. Therefore, the means are not the same. We reject the null hypothesis that says that they are the same. Okay. So this means there's a statistically significant difference in the means between our trainee and our forensic chemist. And we could see that from the graphs, but we didn't have a number. And now we have a number. We can look at these t values and we can say, yes, the t value for our 2 personnel is, the null hypothesis fails, okay? Because our t value is greater than the t critical value. Let's test to see their precision, see if they're the same precision-wise. We know from the graph that they are different in precision. And so this is the F test for equal variances. So our null hypothesis is the trainee and forensic chemist data sets have the same variance, which is the standard deviation squared. So essentially you're saying they have the same standard deviation. We know they don't, but let's look at the numbers to prove that they don't. So we calculate F experimental, and it's a very simple calculation. The t-value test, the t-test is a mess. You got to do the pooled standard deviation. You got to decide when you're using degrees of freedom and when you're using data points. You got to, take the difference of the means. But this one is just the variances, one divided by the other. Okay. And since our trainee could be high or low, we have a two-tailed F test. So once again, our alpha is either 0.025 or 0.975. So it could be low or high. We have an F lower and an F upper. So we need to calculate those. It seems counterintuitive, but the higher F value has the smaller alpha. And you don't have to memorize that or anything. If you just do the Excel formula, you'll get a big number and a small number. You put in the 0.025 and you have the different degrees of freedom. So this is 8 for the trainee and 9 for the forensic chemist. So here we get to put in 2 degrees of freedom, 1 for each. And we get 4.10, and that's the higher of the F values. Then you calculate with the 0.975 and the trainee and the forensic chemist degrees of freedom, and you get 0.23. So how do we do this test? This is the criterion. So if our experimental value, which is S1 squared over S2 squared, is greater than 0.23 or less than 4.10, then do not reject the null hypothesis. But if that ratio is higher than 4.1 or lower than 0.23, then you reject it. So it's got to be between these limits. If it's between the limits, then you can't reject the null hypothesis. So let's see what Excel shows us as these numbers. So here we have the F values. I went ahead and did it with the outlier still in there, and I got 21.39. If I take the outlier out, I get 8.35. So remember, this is the trainee, and this is the trainee without the outlier. Okay. Just to show you what happened when we took that outlier out. Notice it really dropped. It went from 21 down to 8.3. And so then this is the lower F critical value with those degrees of freedom. Again, this is for this value here, because it's got the 9 and the 9. The 0.23 would come from F inverse of 0.975 with 8 degrees of freedom for the trainee and 9 degrees of freedom for the forensic chemist. Okay, and they get a 0.23 there. Same with the 4.03 and the 410. Okay, so our F value, F experimental, is higher than F upper, or left lower, higher than F upper. So since 21.39 is higher than 4.03, the variances are not the same. So we would reject the null hypothesis. Same thing for the, if we took the outlier out, things did not improve. We still have a precision, a statistically significant difference in precision between the trainee and the forensic chemist. We knew that from the graphs, but now we have the statistical support for it. We have actual numbers. So we have a bar, which would be this F critical value, and we have a number that's over that bar. And so we can say without any ambiguity that they have statistically different variances. So we've done all 4 tests. We did the Q test and the Z test on the outliers, the potential outliers. We did the T test on the means of the 2 analysts, and we did the F test on the standard deviations of the analysts. And so the trainee and forensic chemist data sets, these are the sort of a review of the question, are they the same? The null hypothesis is that they are the same in terms of accuracy, but we rejected that with the t-test. So we're saying they are not the same. And then we tested, are they the same in terms of their uncertainty or precision? And the null hypothesis is that they are the same, but we rejected that null hypothesis because of the F-test. We could do these same tests in Minitab, where you just have the 2 columns of data. You don't have to enter any formulas in. This is just a graphical way to get there. You go to stats, basic statistics, 2 sample t-test. You select the trainee and the forensic chemist columns, and you can do some graphs too and hit OK, and it'll give you the t-value, and it'll give you the same answers that we got with Excel. You could also do the F-test in Minitab. Again, stat, basic statistics, and you could come down here and click the 2 variances and enter in the forensic chemist and this trainee columns, and it gives you a nice graphical summary. This is kind of a weird thing to conceptualize, but this is our confidence interval on the standard deviations. So I don't know, I'd have to dig through Minitab to figure out how they're calculating that. This isn't the confidence interval for the % cocaine. This is, here's your standard deviation plus or minus a number on your standard deviation. So your standard deviation could be as low as like 0.6 for the trainee, because the trainee only analyzed you know, a few data points, right? So they're saying, well, we really don't know the precision of the trainee, but it could be as good as like 0.6, but it could also be as bad as 1.7 or so, but it's coming in at 0.93, right? So that was our trainee standard deviation, and this is the confidence intervals on that standard deviation. And here was our forensic chemist standard deviation, and notice that there's this gap here. They don't even intersect. So like the best answer for the trainee standard deviation is not even past the worst answer for the forensic chemist standard deviation. So whenever you see a gap like this, you know there's a statistically significant difference between the two. And then here's the p-value that they're the same. So again, the null hypothesis is that they have the same standard deviation, and this is the probability that they have the same standard deviation. So now it says 0, but really it's only to 3 significant figures or 3 decimal places. So it could be 0.0, like 0.000. There could be a 5 here. If there was a 5 here, it would round up to 1. So we know that it's less than, p-value is less than 0.0005, right? Because if it was 0.0005, they would round up and put a 1 right there. But we know it's less than that. So that's, again, you could do the same kind of analysis in Minitab. Now, we asked the forensic chemist and the trainee to analyze 10 samples. And how do we decide that? You know, why 10? Why not 3? Why not 5? Why not 50? And so that's called a sampling plan. And this is a totally separate category. There's a whole chapter on this in the analytical textbook. There's also a whole thing called the Guide for Uncertainty Management, or GUM. I think I'll have to check Blackboard, but I have that uploaded, or an older version of it uploaded for you to peruse. Or you could look at the ASTM for guidance. There's a lot of guidance in terms of how many lab samples you take. And so for the ASTM, they say you inspect and sort the incoming evidence, and that's how you divide it into lots, okay? So let's say you pull a car over, they look suspicious, the police officer asks if they can inspect the vehicle. Person knows that they're caught, right? So they go ahead and give compliance. Maybe that'll help them later in court. And so the officer pulls up the carpet in the trunk and finds a lot of drugs, okay? Let's just say it's a white powder. So they bring it into the lab, you inspect and sort the incoming evidence. What are you looking for, okay? You're trying to divide it into lots. So if all of the packets appear to be identical, then you've got one lot. But if you look at it and some are tan and some are white, then you would separate those. And you would have the tan lot and the white lot, okay? Because visually you can tell there's something different between these two. But within each lot, then you sample those. So we wouldn't test every bag unless it was less than 20 bags. Okay. But let's say you have 150 bags here. What are you going to do? Do you test them all? I mean, that's expensive. It costs money. Each test costs money. So why spend more money to just get the same answer 150 times when by 75 times you would know that this is a controlled substance and pretty much how concentrated it is. So we need to decide on the number of analyses. Now the ASTM E122 talks about comparing it to the acceptable error and this expected uncertainty. Now this is the expected uncertainty in the sample, and we have really no way to know that. So what is our expected uncertainty? That's how precise the drug dealers are in making these drugs, right? Do they have a 4-place balance? I have no idea what the uncertainty is in this lot of cocaine baggies. Okay, so I think this method is tricky. This is great if you have a knowledge of what's coming in and you know more about it. But it's very difficult if you have a complete unknown. And so there's a bottom line or rule of thumb testing. If you have 20 packets in a lot, go ahead and test them all. Okay. It's only 20 analyses. Most of these instruments have an auto sampler. You can make up 20 samples without wasting a lot of time. But then if you have more than 20, you test 10% of the remaining ones in that lot. Okay. And so this is more conservative than the 10% rule of thumb. So let's say you had, let's do 150 samples, right? What are you going to do? Well, you're going to take those 150 baggies, all right? And you're going to take out 20 randomly. So you have 20. So now you have 130 left over, right? And you test 10% of that 130. So you pull 13 more baggies. Make sense? So out of 150 baggies, you're testing 33. And if you get the right answer or the same answer 33 times, you've characterized the 150. Now, what's the same answer? Plus or minus a reasonable standard deviation. If you look at your data and your data is split into 2 groups, essentially you have, let's see, well, we're pretty much out of time, but let's say you plot your data and you do a dot plot and your data looks like this on those, then you've got 2 lots and you didn't recognize it. This is called bimodal data. And so you would say, well, this is lot 1 and this is lot 2. And so you might do more than your 33 data if you have 2 bimodal data. But if you get the same sort of cluster of data in your 33 samples, then you've characterized that group of 150 baggies and you can move on and write your report. Okay. So this is called a sampling plan. And this is how you decide whether you do 10 samples, 100 samples, or 50 samples, or whatever. But you're probably going to do 20 at least if you have 20 bags. All right, so y'all have a great day. See you next time.